Hi everyone. In this video, we will see the torque slip characteristics of a three-phase induction motor. A three-phase induction motor, which is still being used in many industrial applications. In fact, more than 95% applications are based on the three-phase induction motor. Similarly, we will also see that what are the conditions at which we can get the maximum torque from a three-phase induction motor at the starting, because applications such as electric traction, where still three-phase induction motor is being used as a first choice, and the earlier version of the EVs, electric vehicles, were also being deployed with the induction motor. So such kind of applications require the high starting torque. So therefore, through this video, we will understand how to get the high starting torque or the maximum torque at starting condition. So let's start. To understand the torque slip characteristic of a three-phase induction motor, we have divided the slip characteristics into three reasons. One is this low slip reason, where my slip remains very low, approx to near reaching to the zero, where I can say that rotor is rotating at the synchronous speed, because if my slip becomes zero, that means my rotor is rotating at the synchronous speed. Similarly, the other reason is the medium slip reason, where my slip remains between the maximum and minimum, and the third is the high slip reason, which is can be considered as a starting case, where my slip is approximately near to 1. So here we are first considering the low slip reason, and previously we have also seen that the torque relation, let's say the torque developed by an induction motor is free the standstill EMF of rotor and divided by 2 pi ns, where ns is the synchronous speed in rps, into s times of rotor resistance divided by r2 square plus s x2 naught square of it, where x2 naught is the standstill rotor reactance. So taking this I can say that is remain constant once I have given my supply voltage remain constant, so E2 naught is also remain constant. So therefore, I can say that this is being considered as one constant. So here it is written as the K2, and my torque developed by induction motor remains S times of R2 divided by R2 square plus S x2 naught square of it. Again, taking it from here, I can say that as in the low slip reason, we know that the slip is approximately, we are taking that it is 0. Let's understand that my rotor is rotating at the synchronous speed, which is not possible, still considering that slip is very low. So in that condition, my value of x time x2 naught also become very negligible, and this can be neglected with respect to the rotor resistance. So therefore, my torque will become equals to a constant s times of r2 divided by r2 square over here, and therefore it is also, again I can say that if my rotor resistance is also again remain constant, so the torque in this condition is proportional to slip. If I'm taking that K2 divided by R2 is one more constant over here, so if this K2 divided by R2 is taken as one more constant, let's say K3, so in that condition, my torque becomes proportional to the slip for low slip reason particularly. So therefore, I can say that for the low slip reason, the torque slip characteristic will have the curve of the straight line. So this is about the low slip reason. Now we'll take the medium slip reason. let's take the second slip region, which is the medium slip region, where my induction motor runs. So therefore, in this condition, my slip becomes significant. It is not having the approx 0 value. So therefore, the value of x2 naught becomes significant as compared to the rotor resistance R2. So therefore, the R2 can be neglected. So neglecting the R2 in this torque expression will give me a simplified expression of the torque if my motor is running in the intermediate slip value. So therefore, my torque becomes proportional to 1 by Sx, which Hx is the some slip value where my induction motor is running. So in this region, the slip characteristics is inversely proportional to the slip value, and therefore it is having the hyperbolic curve. In this region, my graph or the characteristic changes from one form to another form. It was from the linear graph to the hyperbolic graph, and this is the reason where it passed the maximum torque produced by the induction motor, which is also known as the pull-out torque. And the pull-out torque is 2 to 3 times of my full load rated torque of induction motor. So therefore, induction motor has the capability for the short time overloading. In case if it has happened, then induction motor can bear the short time overloading. Therefore, it gives the 2 to 3 times of the torque, maximum torque from the full load rated torque. Similarly, my starting torque of induction motor is 1.5 times of my full load rated torque. However, there should be overloading protection should be deployed for the induction motor in case the overloading happens for the greater period of the time. The third slip region is the high slip region, where I can say that my slip is approaching towards 1, where this is the condition where my motor is getting standstill. So as I increases my slip further, which is greater than my value of SM, where I'm getting the maximum torque produced by the induction motor, or also known as the pull-out torque, the SM value can be achieved by R2 and X2 naught. At this slip value, I can get my maximum torque from the induction motor. After this slip value, my torque produced by the induction motor gets reduced further, and if there is overloading further, the eventually motors is going to stop. So therefore, in this region, my motor is eventually going to stop, and my motor generally runs from low slip region to medium slip region, in between that. So it is also known as the stable region of operation for an three-phase induction motor. So taking all three regions over here, now we can plot the torque slip characteristic. So this is my low slip region where my curve is almost linear. We can see that this curve is almost linear over here, and here this is the intermediate slip region where I can see that my curve is hyperbolic, and the high slip region, eventually my motor is going to stop over here when the slip becomes equals to 1. The motor running condition or the motor speed will become equals to 0. So at this point, as I've told you, that intermediate slip region will also have the maximum torque or the pull-out torque produced by the induction motor. So this is the slip value where the induction motor produces the maximum torque, the SM, where SM is nothing but the ratio of R2 divided by X2 naught over here. And this is the operating region of my of my induction motor, three-phase induction motor. And this region is also known as the stable region. This region eventually becomes the unstable region because my speed of the induction motor is eventually going to reduced as I'm going to further increase my slip value. So therefore, this is the stable region and this is the unstable region, and my induction motor generally operates between low slip region to the maximum here, the this is becomes my operating reason of my induction motor. So now taking the same characteristics in a different perspective over here, instead of slip starting from 1, I can say that slip is 0 over here. So this is again the maximum torque, is also known as the pull out torque. So OA, this region from here to here, is known as the stable region where my induction motor operates. A to B is the unstable region, which we have already seen it. This C point is the full load torque which is being produced by my induction motor, and as I've already stated that the maximum torque is 2 to 3 times of my full load torque. So therefore I can say that induction motor has the short time overloading capacity over here, whereas the B point shows the starting torque. However, this point, which is here shown as the B, the starting torque from an induction motor, this can be altered or this can be modified by using the external rotor resistance being inserted, and therefore we can get the maximum starting torque in case of the induction motor just by putting the external rotor resistance in the induction motor circuitry, because my slip at which I get the maximum torque is equals to R2 divided by X2 naught. So therefore starting we will have the slip will be equals to 1. So therefore this is shows the starting point of my induction motor. This is the starting torque over here. So in this condition, the R2, if I can make R2 rotor resistance become equals to the my rotor standstill reactance by some mean, so in that condition I can get the maximum starting torque when the slip value is equals to 1. And this is only possible in case of the slip ring induction motor, because the slip ring induction motor has the arrangement where I can insert the external rotor resistance, and which can be cut off as my motor picks up the speed, because initially at the starting I need a high resistance in the rotor circuitry, but once my motor picks up the speed, the slip value also gets reduced, and therefore the value of SM is also gets reduced, and then my rotor resistance need to be cut out from the external circuitry, and which is only possible in case of the slip ring induction motor. Here I have taken the 4 different curves to understand that how my torque slip characteristic gets changed with respect to the external rotor resistance if I increase my external rotor resistance. So this is the condition where I'm getting the maximum torque over here. So this is the condition where I'm getting the maximum torque. This and the value at which I'm getting the maximum torque is equals to the SM. So the first curve, let's say this is my R21, and the second curve where I'm getting the maximum torque at the different slip value, and let's say for this the rotor resistance was R22. Similarly, the third curve where I'm getting the maximum torque further at different condition, let's say this is R23, and let's say the fourth curve where I'm getting the maximum torque when my slip is equals to 1. So this is the condition where I'm getting the maximum torque in the starting. Therefore, at this value and for this condition, the rotor resistance becomes equals to my standstill rotor reactance. So I can say that in this condition, the R2 is the maximum, then R24, R23, then R22, and then the lowest value of R21. So I hope we have understand that how increasing the rotor resistance by some external means changes the slip value at which we get the maximum torque, which is very handy for such applications where I need the high starting torque, similarly like electric rail, or let's say the electric vehicle also. So let's take the torque slip characteristic further. more than the slip value 0 to 1 only. So this is a reason, the motoring reason, which we have already seen it, where my slip is being changed from 1 to 0, because here my speed is synchronous speed and my slip value is 0, and this is my starting slip value, and this is the operating reason of my induction motor. So this is my operating reason for a three-phase induction motor. So this is, we have already seen it. Now let's take it further. What happens if my slip becomes negative, where my slip is negative or less than 0? So in this condition, a very interesting phenomenon happens. Somehow, if I can make my rotor rotating more than the synchronous speed, so in that condition, my rotor speed is more than the synchronous speed and the slip becomes negative, because slip is nothing but ns minus nr upon ns, where ns is the synchronous speed and nr is the rotor speed. The only way by the slip becomes negative is if my rotor speed is more than the synchronous speed. So in that condition, instead of motoring operation, my machine, induction, three-phase induction machine, will behave as induction generator. So this is the reason where uh, my machine is rotating as the generator, and this phenomena is being used for wind power application and also for regenerative application, regenerative braking application. So regeneration happens due to this reason. Now the question is how we can make slip negative value, or how my rotor can rotate more than the synchronous speed. Let's understand with one example. I am driving an EV, and if I'm going the downhill, then my rotor is, which is coupled to my wheel, so it is rotating by itself because of the gravitational pull over there. And in that condition, if by manipulating the supply frequency which is going to the stator, because the synchronous speed is nothing but the 120f over p, and if I can manipulate by somehow the frequency over here, if I can reduce the frequency over here, the rotor is rotating by itself. However, the frequency, reducing frequency, can further reduce my synchronous speed. So this synchronous speed should be less than the free rotating rotor. In that case, the slip becomes negative, and by doing so, if I'm going downhill over there, so that uh, energy is being produced by my EV can be fetched back to my batteries, which is also known as the regeneration or the regenerative braking. The similar application is also being used, the wind power applications, where my rotor is directly coupled with the wind turbine blades, which rotates according to the wind speed. However, the wind speed is fluctuates, and so therefore we need to have the control over the synchronous speed, and then from there we can produce the generation mode from the induction machine. So I hope it is clear that the how we can get the maximum torque at the starting, and how we can make the regeneration happens through my induction machine. See you in the next video. Thank you.